Welcome to today's lecture on electric dipoles and field intensity. This is an important topic in Class 12 Physics Electrostatics. Let's start by understanding what exactly an electric dipole is. An electric dipole consists of two equal and opposite charges separated by a small distance. Specifically, we have a positive charge plus q and a negative charge minus q separated by a distance of 2a. The dipole moment vector, denoted as p, is defined as the product of the charge q and the displacement vector L, which points from the negative charge to the positive charge. Mathematically, we write this as p equals q times L, where the magnitude of L is equal to 2a. Now, let's examine the electric field created by a dipole at different locations. First, let's consider a point P on the axial line, which is an extension of the dipole axis. If the point is at a distance r from the center of the dipole, and r is much greater than a, the electric field at this point is given by E axial equals 1 over 4 pi epsilon 0 multiplied by 2p over r cubed. The direction of this electric field is away from the negative charge toward the positive charge, which is along the dipole moment vector p. Next, let's consider a point P on the equatorial line, which is the perpendicular bisector of the dipole. If the point is at a distance r from the center of the dipole, the electric field at this point is given by E equatorial equals 1 over 4 pi epsilon 0 multiplied by p over r cubed. The direction of this electric field is opposite to the dipole moment vector p. Notice that the field on the axial line is twice as strong as on the equatorial line at the same distance r. Now, let's consider the general case of the electric field at any point in space. Let r be the position vector of point P from the center of the dipole, with unit vector r hat. Then the electric field vector E at point P is given by E equals 1 over 4 pi epsilon 0 multiplied by 1 over r cubed times the quantity, 3 times the dot product of P, and r hat multiplied by r hat minus P. This formula gives us the complete electric field at any point in three-dimensional space. Let's visualize the field pattern created by an electric dipole. In addition to the electric field, we can also calculate the electric potential due to a dipole. The electric potential V at a position r due to a dipole is given by V equals 1 over 4 pi epsilon 0 multiplied by the dot product of P and r hat divided by r squared. Unlike the electric field, which falls off as 1 over r cubed, the electric potential falls off as 1 over r squared, which is still faster than the 1 over r potential of a single point charge. Finally, let's discuss what happens when we place a dipole in a uniform external electric field E0. When a dipole is placed in a uniform external field, it experiences a torque given by torque equals P cross E0. This torque tries to align the dipole moment P with the direction of the external field E0. The potential energy of a dipole in an external field is given by U equals negative P dot E0. This is minimum when the dipole is aligned with the field, and maximum when it's antiparallel to the field. Let's summarize the key takeaways about electric dipoles. First, the electric field of a dipole falls off as 1 over r cubed, which is much faster than the 1 over r squared dependence of a point charge. Second, on the axial line, the fields from the positive and negative charges add, resulting in a field twice as strong as on the equatorial line, where they partially cancel. Third, in an external field, a dipole experiences a torque that aligns the dipole moment with the direction of the external field. Understanding electric dipoles is crucial for many applications in physics, chemistry, and engineering, from molecular structures to antenna design. The concepts we've covered today provide the foundation for understanding more complex electrostatic systems.